So I could start with, hopefully when I'm done, you will have some ideas about what a grand challenge is. We need to take my picture down off of there. Because I'm going to talk a bit about big data and advanced analytics. And I think today, most people would say it's a hot topic in the industry. Some say it's overused, maybe even abused. But I think what we're trying to do is deal with the fact that all of our organizations, the data has grown. It could be your internal organization data, it could be your customer data, could be event data that exists out there that has some form of impact on your organization. And so we're really trying to figure out how do we get the most value for that data. And I think the answer is we're starting to. So back in May, in Moore, Oklahoma, everyone will remember that we had an Ef5 tornado hit. I happen to live in Dallas, so this hit home, close to home. And what happened was there was 36 minutes of warning due to improvements in the predictive models. 36 minutes is 24 minutes more than the typical warning that we get for tornadoes. That's the difference between life and death. So when people say, you know, is it really worth saving all this data? Is it really worth investing in, you know, the analysis, especially when it's hard, right? The skills are different, it's hard to do. I say, well, in this case, it's a matter of life and death. But we're not even done, because NCAR is wrapping up an experiment, actually this weekend, I think it finishes, where they're going up into 7 miles above the earth to try to look at more higher level atmospheric data, because what the hypothesis is that where the data models errors are coming from today to improve the predictability of severe weather is up at that 2 to 6 mile atmospheric layer. So they're collecting data to bring that down and do the analysis with ultimately hoping to get up to 8 hours notice for severe weather events. And when you look at what they're trying to do, it isn't all that different than what we do for hurricanes in the improvements in hurricane predictive models. So there's a lot of learning that can be done and have tremendous impact on organizations. There are an abundant number of cases also in commercial enterprises. So I want to talk about some industry examples and then specifically what we're doing at Intel that I think is extensible to other organizations. And I evidently figured out how to work the clicker. So UPS, UPS moves packages. And what they're doing is trying to automate effectively that last mile. So they have implemented smart labels. And a smart label, because you know people are printing, whether you're printing as a commercial enterprise, you're printing your label in your facility, or you're printing from home, and they're creating these smart labels. And what they know from historic data, they know a lot about exception packages, they know a lot about routing. And so the process for that package distribution starts when the label is printed before the package ever arrives in UPS hands. And what they've done is use that information to do better loading of their trucks and then route optimization. So they avoid things like left-hand turns, waiting at red lights, traffic congestion patterns, and they've saved between 20 and 30 million miles, which equates to 3 million gallons of gas. So there's money in that, but also there is carbon footprint reduction in that. So anybody that's moving, that's a supply chain problem. Anybody that's moving anything can think similarly about that distribution. And then I think almost everybody knows on President Obama's campaign in 2012, they used this micro-targeting. So they took zip codes and they looked at voter profiles, and then they tried to determine who was persuadable in that zip code, and they used that for campaign fundraising, but also how to apply the fundraising dollars. I think a lot of people believe, and I'm one of them, that made a huge difference. I would say it made a difference in 2008, and it made an even bigger difference in 2012 because they got better as they went along. And then GE is looking at, their vision is fix it before it breaks. So they make a lot of big things, airplane engines, hospital systems, energy systems that cost billions of dollars. And when they go down, they're mission critical. If the airplane doesn't fly, their airlines get no revenue. And so what they have, the vision is really about their customers' business, enabling their customers' business to operate in the most effective manner. And so they're doing these predictive models about, they have the machine specifications, they have the use patterns, and then they predict when they have a failure, and they actually send out repair before that failure occurs to help their customers' business do better. Okay, so that's meant to represent how Intel IT is looking at how we apply big data and analytics on top of big data to help Intel. I think it helps, though, to start with a bit of an understanding of where Intel is as a company. So we're in the midst of transforming. We've historically been a PC and server company, and by far the market leader in that space. We're entering into phones and tablets. This happens to be one of my new Intel tablets. But we're not the market leader there. And the market is starkly different. So the time to market matters because a phone life is about half of a PC, meaning we have to get products to market twice as fast. The price of a phone is significantly less than the price of a PC, which means, so these have broad-based implications. And so we're looking at where do we use what we know and what's happening in the industry to help the company get better. And we've used this model that really sort of starts from, we've been a data sort of oriented company, and we always do root cause analysis. And what happened and why did it happen? And we're trying to take that and move that forward to say what will happen and how do we make it happen. Really move into that prescriptive and predictive modeling capability. So some examples. We have Intel Inside program. It's the largest marketing and co-branding program out there available to OEMs and systems integrators. So we've been growing this program, and of course with that comes claims. And so we were looking at this increase in manually auditing the claims, and it was causing delays in payments, which doesn't make our customers happy. So we developed a machine learning model based on reading the claims. They're all digitally submitted, reading the claims, looking for incomplete areas, looking for duplicate claims, looking for fraudulent claims. And we made the machine learning model get better with each iteration. So if there was a new form of fraud, it would throw it out as an exception. And the results were we were manually auditing 20% of the claims. We're now confident that we can audit 7% of the claims, so it significantly reduces the manual work involved. And in the first year, we've saved $30 million, which we thought would be mostly from fraudulent claims. Turns out that wasn't really right. It was mostly from duplicate claims. Because we were so slow to pay, what happens when you think you are owed money and you're not getting it? You submit another claim, which it just kept compounding. So now that we can see this stuff, we greatly reduced the number of claims because all those duplicates are gone, as well as we avoid paying duplicate. So I would say this model is extensible to insurance claims, warranty claims, any form of rebate claims, and you can do the analysis of that, create that segmentation, and then really start to look at manually only things you need to look at and increase the payment capability. A second example is in our post-silicon validation, if I can get this to move. I'm trying to be patient because it looked like before I was pushing too fast. There. So I said product time to market is really important to us. And the last step before high volume production is what we call post-silicon validation. And what we do there is we test the transistors. So on a wafer, which is our unit of output, there are billions of transistors. And if the circuit is open, we need current to flow. And if the circuit is closed, current shouldn't flow. And that's what we test in post-silicon validation. But you have to do that on billions of transistors. It takes a long, long time. So we're trying to cut time to market. And when we find errors, historically what we do is we send it back to engineering. They would make some changes, and then it would come through the process again. We manufacture the parts, we test them, and then we go. And what we did with this was we also created a machine learning model. And it took all the historic tests that were done on those parts, plus the engineering changes, to create a model that says you should test these specific transistors. And the results were we got 25% greater coverage of the wafer versus the random sampling technique we were using before. And we were going to cut the time to market by up to 50% for that step. And usually it will take us 5 quarters for post-silicon validation, and we think we can drop at least a quarter out of that cycle time, which again, when you think about the type of products and stuff that we bring to market, that can be huge benefit to Intel. Another cost reduction was in our manufacturing process. When we take it, that wafer then gets cut up into individual chips. We call them die. And then we take the die and we put it on a package and we bond it in some way, and that becomes the product that we sell. Well, that package that we put it on costs up to $40. And what we were doing was we would get the die cut from the wafer, we put it on the package, and then we test it again before we send it out so that we know every customer gets a good die. So, and we find failures in that process. So we said, what if we could test earlier before we bond that to the package? And we had all this historic information that we weren't using about what happens at the die, what happened in post-silicon validation, where were what was tested. We started to use that, and we created then individual test patterns. Instead of doing random test sampling, we do unit level testing on the die before it's bonded to the package. And the first product we did that on, we saved $3 million. And that isn't a lot of money for the amount of money that we generate for a given product. So the second product, we took the same machine learning model and we kept the data from the first product, we saved $20 million. And the third product, which we're in testing now, we believe is $100 million savings. Why? The data set's getting bigger. It has more knowledge about what tests work, what tests don't work. And so the more products we do this on, the more data we have, the better the outcome. So we think that, ultimately, when we get all products through this cycle, it's several $100 million of benefit to Intel. So, but we also want to grow revenue at Intel. And because we have new products, we have new channel partners and new customers. And we're adding a lot of them. But of course, like everybody else, our budget is tight. We didn't give the sales organization that much more money to pursue these new customers. So a sales organization, traditional model for our channel organization, they were assigned by account and by territory. So we said, well, what makes the difference between a good sales call where someone buys something from us and where somebody doesn't buy? And the best salespeople can tell you that. So they told us, and we said, one of the things was that they have to know something about Intel architecture. They have to know about what products are available and then how to use Intel architecture. We said, well, where do they get that? They get that off our website. So we said, let's look at our web logs. We can tell who's downloaded what information. Do they have enough knowledge inside their organization in aggregate to actually build a product with us? And then they have to have a certain amount of R&D. We said, D&B has that information. And so we combined what was publicly available information with our own web logs to create a model that said, these customers have the highest propensity to buy. Reassign your sales resources in order of highest propensity to buy instead of by account and by territory, and you'll get better results. In 1 quarter, we got 5x improvement in those sales resources that were assigned by highest propensity to buy versus by account. And in 1 quarter, they generated $2 million of incremental revenue. We're now cutting over all of our channel sales to a highest propensity to buy resources. It makes our sales team a lot more productive. So you can say, well, those are great results, and we're very proud of those results, by the way, but we're also feel like we're just scratching the surface of what's potential. And so we've got some other initiatives. The last one is probably, I think, the most interesting, which is to say that the new user experience, it's no longer about a graphical user interface. It now becomes a pattern of use. So I can tell with facial recognition, with great sensors, I can now tell a lot about user behavior. And I can tell even what mood you're in, or correlate the events that you have a meeting, it's titled Ops Review, therefore we should load up the PowerPoint that has your operational indicators on it. And so we're trying to create a completely different user experience for our Intel employees to make them more productive with using a dynamic UX, taking into account all of the events and their time and location as well as their mood to create a different type of experience. That is just in the research phase, by the way, but if we were successful, we think it will be great benefits. So my examples, I think, can be broadly applied to any organization. Everyone's business problem would be slightly different, but my message would be it is important to get started. And find those quick wins. If you find the small wins, then they build to bigger wins. But I also think you have to spend just that model, what happened, why did it happen, is important. But you have to dedicate some time, you can decide what the percentage is, to what will happen and how do we make it happen for your organization. So it isn't leave behind the old and move completely to the new, but it is to get to both a shared view of that. These skills are scarce, and you have to start somewhere. Everybody has some form of data scientist in their organization, and everybody has not enough. There are organizations out there where they'll run predictive models for you, they'll run experiments for you, so I say that's a renting of the skills. And then I think you have to build them over time. So there's no silver bullet here. Skills are a hard problem. But I think ultimately we're in this state where we have to experiment a little bit with all of them. And then I think the thing that we've learned most through all of our work is that correlation's important and will tell you something, but it does not mean causation. And when you really get to trying to make things happen for the best outcome that you're seeking, you have to get to causation. And so looking back into what are the causes become a part of those prescriptive models that we build for the future. So my view is that the IT profession, right, is at the center of what these changes are. And there's probably no better organization but IT, I might be slightly biased, to lead these types of changes. Big data, analytics, they're board level, CEO level agenda items, but they don't know what to do with it. It's what the IT organization can bring that level of understanding and that roadmap of how you take that journey that will help the organizations get better and truly be the catalyst of change and unlocking the potential of what your data has inside your organization. So, thank you.